Hey, okay, welcome to lab here on the Wednesday of the second week. So this is the end of the week 2. So this would be our fourth lab, excuse me. Yeah, fourth lab, because we didn't have one the first day. And we're going to do one titled Work and Energy. And I will tell you that the idea of work and energy is in chapter 7. We haven't quite covered that yet in class. That's what we're going to do after the exam. And so this lab is kind of designed to be one that I might call it kind of an introduction. In other words, it doesn't try to explain everything about work and energy. It just kind of gets us started. So I think you're going to have quite a few questions in your mind about work and energy, but that's okay. What hopefully you'll be able to do is just kind of get a little bit about work and energy out of this lab here. And so this lab has 2 parts, just kind of like the last lab. And so actually, why don't I start here on the board and say, okay, I'll put some information here about part 1 of the lab. And over here, I will put some information about part 2 of the lab. And on the far board here, I'll go ahead and just say here that we are going to learn that what we're going to call potential energy, and so I'll just put PE, gravitational potential energy, is the energy associated with an object as you put it up higher and higher. In fact, we're going to learn that work is force times distance. And then in this case, the object, and I'll just kind of pretend with my Clorox wipes here, okay, this is my object. And so if I put this object, say, up on a shelf, what I'm saying there is it has a certain energy. That means if the shelf broke or it slipped off the shelf and it would fall, there would be a force on it, and that force would equal its weight. So there's the mg. And the distance it would fall would be its height. And so this is going to be our working equation. And this is the part that I was saying that I'm not going to fully explain this equation until we get into chapter 7. But what I am going to do is kind of give you what I just did, a rough background of this equation. Our job here in today's experiment is to kind of validate that equation. So let me emphasize. I'm not trying to prove that equation. That day's coming. What I'm going to try and do is validate it. And so just like yesterday when we did the force and motion, we were trying to validate Newton's second law. We didn't try to explain how Newton came up with that second law. We were starting with that, and then we validated it. We hopefully were showing that net force was directly proportional to acceleration and mass was inversely proportional to acceleration. So we're going to hopefully see the same thing here. So our 2 variables that we can change when we have an object is what is the mass of the object and what is the height at which we let it fall. Okay, so I will say that explains over here why we have a part 1 and a part 2. Because in part 1, we are going to vary the height. We are going to drop things from a different height and then measure how much energy is associated with that drop. We will then make sure that we don't change the mass. And that way we will know that if we measure a lot or a little or kind of in between amount of energy of this object, that the amount of energy either increases or decreases based upon the change in the height, not on the change of mass. And so part 1 really is asking how is energy related to height, which explains why we have a part 2 then. Part 2 over here is we are then going to vary the mass, but always then keep the height a constant. And so that's our goal here, is to see each one separately. In this case, how does energy change when you change its mass? And on this one, to see how energy changes when you change its height. And if we come back over here to this equation, like I said on the last lab, we won't use this equation. We're trying to validate it. That's that circular reasoning argument that we had in the last lab. But what we will do is we will hopefully collect data where we get height and energy, and we measure it some way and separate from this equation, and then the data that we get hopefully has the same pattern that we would have got had we used this equation, and hence we are validating this equation. And I would even say what makes today's lab a little bit easier than last time is that both of these variables are in the numerator. Both of them are proportional. And so hopefully, and maybe I'll help cut right to the chase, you're going to be asked to do two graphs. And in part one, you're going to be asked to plot the energy on the vertical axis. Hey, Sean. And you're going to also ask to plot the height then on the horizontal axis. And of course, the equation says they are proportional. So hopefully what you will see, and I think we do it 5 times, 1, 2, 3, 4, 5, is you'll see that. And so like our discussion on yesterday, hopefully you'll see they are proportional. And I'll just point out again that a straight line, or nearly a straight line, that goes nearly through the origin is what we need to prove if something is proportional. And that's what we talked about yesterday. We also did an inversely proportional yesterday. We don't have that. That's why I said this is a little bit easier, because on the second piece of data, you will make a plot. And again, you'll be plotting energy on the vertical axis. And then over here, you'll be plotting the mass. Technically, it's your mass added to your apparatus, which is why this graph kind of confuses students at some times, because it's 0 right there, and so your first plot is 0 added. And I'll explain more about that in detail. But just trying to give you the big picture, and then again I'll mention this back here on the board here, is that without justifying this equation yet, which like I said, we will justify this equation. And then we'll do that in class. But for today, let's just take, this is the equation for what we call gravitational potential energy, and let's just see if the equation can be validated. Let's just see, is the energy proportional to the height? And then part 2, is the energy proportional to the mass? So there's 2 parts. So if you haven't already, go ahead and get that lab manual out. Either you print a hard copy because you're going to scan it, or because you got to write down some numbers and put it in, or just do the, on your screen, the PDF. But looking on page 27, let me move the apparatus out of the way and just show you page 27. You will see that there is a part 1, and you can see then there's some stuff here about height and energy. And then there's a part 2, which you can see there's something here about mass added and energy. And this is what you and I will do together. And so you and I are going to, like all the other labs, be thought of as a lab partner. I'm going to collect data, you're going to write it down, and then from that you're going to do your graphs. In fact, as I look at the other pages, now here's the page 29, which would it be, I guess, this one here. This would be the energy, although as you'll see in a moment, the way we measure the energy is by the distance the rod moves, so that's on the vertical axis. And then over here, this is the mass that is added to our, what we like to call our driver. Page 30 is this graph here. Again, we'll measure energy, and we'll measure that by saying how far did the rod move. I'll show that in equipment, and this is how far it fell. But as I said, in both cases, hopefully we will get a straight line on these two. And so, unlike yesterday, we won't do a third graph. We won't need to. We don't have that hyperbola. We just got two straight lines, and so we prove that it's proportional to both. In fact, that's kind of the answers to these homework questions, or these into the chapter questions. They ask is it proportional, or what is it? And you're supposed to say it's proportional, and then eventually it's proportional to both. And so they're pretty straightforward questions on here, except for maybe the first one. So I'll come back to the first one here. But let me just show you then the equipment. Here's the idea of the equipment. This is the driver. This is the object we're going to drop, and I'll just let it go and it will fall. And what it will do is push this rod down through this piece of plastic, which I can adjust the friction here. Now, before we started the lab, I adjusted the equipment. So I'm not going to change this friction, and that's part of this harder first question that I'll come back to here. We want to make sure that the friction remains the same, and there's a little question here about that. So keep that in mind, that the friction needs to stay constant. Sadly, this equipment, and if this was face-to-face, or even if it's not face-to-face, I would say notice it's just kind of homemade, handmade equipment, and it gives us okay results. I think it's probably the least accurate equipment we have for the semester. So good or bad, let's just see what we get. It's also why I like to say, just in case our data doesn't come out good, because of our little homemade equipment, I like to always point out this first, that it's supposed to be proportional. You're supposed to see a straight line for both of these. Your conclusion is they're supposed to be proportional. And so if you get something that's not quite so pretty as a straight line, totally understandable. And I'll be curious to see what I get. Normally, I don't actually do all of them. Normally, I just say, okay, students, good luck. And I walk around and I see what they have. And they don't look like straight lines. But I tell them, look, take a ruler, make it a straight line. It's supposed to be a straight line. Or at least half of them don't look like a straight line. The other ones do. So some of it's equipment. Some of it is students not being careful enough. I don't know, but let's see. I'll try to be careful, and hopefully I got a decent one. I looked through a bunch of them, and my guess is this is a good one. It's hard to really tell until you get some data here. Okay, so I'm going to go ahead and, as I said, start filling this in. And so you can see it a little better here. I'm going to put here, and you'll see a big box here that says start off with an initial drop of 4. And then it gives 3 small boxes, and then it says average those. So this is grayed out, and this is grayed out. Then we're going to actually measure the energy by what is over here, which says how far did the rod move. And so, and I guess I should have put over here, this is the fall. How far did I drop my object? And so when you drop it from these 3 different heights, it will move the rod 3 different heights, and then you can take an average. And you have that same chart repeated for an 8, so 1, 2, 3, average, part of the gray. Maybe I made that box a little too big. 1, 2, 3, average, part of the gray. Then you'll see it asks you to do a third time. Here's the 12, and it's got another 3. So 1, 2, 3. This is all grayed out. 1, 2, 3. And grayed out, and then average. Grayed out, grayed out. And I'll just continue with my chart over here. Then there's a 16, and it leaves enough room for 3. And then finally the last one is a 20, which leaves a room for 3. So 1, 2, 3, 1, 2, 3, average, average. Oops, forgive me, I'm going to get rid of that. Double bar, and then we'll go 1, 2, 3, 1, 2, 3, average, average, grayed outs, grayed outs, grayed outs. I should have put all this on the board before I got started. Didn't realize it would take quite so long here. All right, so I'm going to fill these in, and you're going to, of course, watch me do the lab, and then you're going to write these down. And we'll write them down together here. All right. And then, of course, you'll do the calculations. Now, again, let me just show you one that's facing you so you can kind of see it. But I'm ultimately going to turn it towards me, if you will. Or maybe kind of a, well, I'll see how far I get. I'll leave it towards you. Okay? And let's start by dropping it a small height. And that's where this 4 comes into play. Well, what the 4 would mean, and so if this was a face-to-face class, I would say go ahead and take, and I like to have my little marker on this side, is take your driver and lift it up 4 centimeters. Okay. So I'm going to put my little marker right here, 4 centimeters. And if you watch this, and let me just make sure my nail is reset. Bummer, it wasn't. So let me redo the 4. There we go. And so if I were to lift this up right to the bottom of that stopper, and now it is 4 centimeters above, and I let it go, and so I just pull my hands apart. I don't throw it up or throw it down. I just let it drop. Because it hits the nail and moves the nail, the actual drop of the hammer is more than 4. And so that's why in this chart over here, we're going to end up putting a number right here that is greater than 4. And so I'm going to measure it here. And so this says 5.7. Now that seems like a little much, but that's what I got. Okay. So let's try it again. And because things don't work all that great, we want to do it 3 times and kind of get an average. So let me do it a second time. All right, so I'll put it here and let it go. Now, how far did the hammer fall this time? 5.5. And so I'll put 5.5. And if I reset it for a third and final time, so lift it up, let it go, 5.5. And so I would say that these 3, and this is where the average is going to come in. And let me not do the average, but let me encourage you, get your calculator out. And add these 3 together and divide by 3. And you will get, I probably do that one in my head. Let's see, they differ by 2. And so it'll be, is that 5, 7, I think? All right, I said I wasn't going to do it, but now I'm curious. So 5.5 plus 5.5 plus 5.7. Add them together, divide by 3, and it's 5.57. All right. So there is the average distance it fell, all right? What you're going to plot then, and remember I had to erase it here, so I'll put it back over here, is the distance it falls. You would be plotting that average, 5.57. And then you're going to be measuring how much energy it has. And that energy is based upon how much did the rod move. And we really have that number. We don't have to go here and measure it. But we can get the distance that the rod moves because the difference between here and here would be how far the rod moved, right? We set this up so that the driver would fall 4 centimeters, then it hits the rod and it pushes it down. And so if the whole distance it fell was 5.7, it did that because it pushed the rod 1.7. 1.5 and 1.5. Okay? And so you're going to want to average those and get 1.57. And so over here, you're going to want to put that then in your graph at 1.57. And so we're using the distance that the rod moved as a kind of measurement of how much energy it had. Now this is a good time then to maybe address the harder of these 4 questions, and it's this first one here. Because it says here, we assumed that the distance the rod moved was really proportional or a measurement of how much work was done. Why can we justify this? Why is this reasonable? And so I would say, and I guess I'd have to come all the way back over to here, since work is force times distance, in this case, the force on that rod is the friction, and in this case, it's this part of the machine right here. It's the friction in the rod, and then multiplied by the distance it moves. Okay? So I would argue here that we're not really measuring energy because we're measuring distance. However, that's what this question is after. How can we then justify using the distance the nail moves as the energy? And the answer to that is because if we don't change the friction for the whole lab, then the distance it moves is directly proportional to the work. And you might have a little trouble with that question, is why I thought I would bring it up, because we haven't really done this yet in class yet. But again, hopefully, most of this, notice most, I didn't say everything, but most of this will make sense. And then eventually will make sense as we move into chapter 7 in class here. So I completely understand that, you know, things might be a little fuzzy here because we're doing the lab first. But it's designed that way. It's not like we're making a mistake. It's designed that way. This is just a good introduction, and so it's kind of nice, as I said, to maybe not really justify these equations or explain these equations, but just confirm them with our data, and we'll get that. Well, let me move on to a little higher level. Let me move over here to dropping it 8 centimeters. Now, I should be careful with that phrase. I'm not really dropping it 8. It's going to be more than 8. It goes 8, then it hits the nail, or a hammer, a rod, and then it pushes that rod a little bit. So, if I come over here now, and I put this little stopper at 8 centimeters, okay? And I check the rod there, and I put it up here and let it go. I get a distance of 10.7. So here is the distance the driver fell, 10.7. Which, by the way, then would mean the rod moved 2.7. And so then I will reset it and do an identical measurement. Like I said, hopefully the average of these will be pretty good. And that's 10.5 again. No, not again, 10.5. Let me just double check that. Because I said again, but yeah, that's 10.5. And so that's 10.5, which means it moved 2.5. And then the third time, just to get a decent average here, as you and I are working together here as a team. And there's our second height. And this would be 10.6. 10.6, which means it moved 2.6. Now this time I really won't do the average, but what you need to do then is get the average and say, okay, on average, if I drop the driver this much, the nail moves this much, and then you need to take that and you need to put it in to here. And so now we get more energy, but we also drop it from a greater height, a greater distance. And so that's this idea. So let me move on to the third level. And the third level is to set the stopper up here at 12. And so if I hold it up and let it go, and then make a measurement, I get a 15.3. And so that makes a 3.3. If I do it a second time, yeah, I like that better. 15.7, which makes this a 3.7. And I think I'm going to do that first one again. I didn't say anything, but I could feel that I just didn't drop it right. My hands I didn't pull out. I was a little sluggish. So let me do number one again. So here, just pull it to the side. Yeah, see, that's a 15.7. All right, so that's a 15.7, which means that's a 3.7. All right, and so let me do the third measurement for this third height. And so I'll come up here, pull my hands just out, not down, because that, that kind of blocks it as it's going down. And so I get a 15.8. So 15.8, which means it's a 3.8. And again, let me just say, I'll let you calculate the average of these two, and then hopefully you'll put something in like maybe here. And again, now you'll have 3 data points. And again, they're beginning to hopefully see a straight line there, because again, this is the whole point is, and I'll point out this back here, we're trying to see, is it true about this equation? Is this equation really saying that the energy is proportional to the height? And so if you double the height, you double the energy. If you triple the height, you triple the energy. If and so that would mean a straight line. And so I hope you're beginning to see that. All right, let's go to the next setting, the fourth drop. And so the fourth drop is put the stopper at 16. Okay. And so I'll put the stopper here at 16. Lift it up and let it go. And it fell a total of 21.0. And so 21.0 there. Let me reset. Try it a second time for this fourth height. And I get a 20.9. Oh, and I guess I do that. It wouldn't be too hard. So this would be a 5.0. And then this would be a 4.9. Okay. And looks like I got one more at this height. And one more. And it looks like that's a 21.0. So 21.0 would then make a 5.0. So same idea, get the average of those two and put them in your plot. And again, hopefully you're seeing really the results here. The goal is to say that the energy is proportional to the height. You double the height, you double the energy. You triple the height, you triple the energy. All right, one last set of drops and we'll be done with the first half. And let's set this at a vertical starting drop of 20. And this is the one, keep your fingers crossed, where these loosen up over time, and if they get too loose, then the rod hits the bottom. Ah, good, and it didn't. And so we often have troubles with this last one, but this is looking pretty good. This is a 26.1. And so if I go 26.1 and subtract the 20, that means the rod moved 6.1. And let's drop it a second time. Reset. Drop it a second time. And I'm not going to measure that one. It wasn't too bad, but I felt like my hand was a little sluggish coming off, and I didn't drop it well. Pull my hands out like that, so we got a free fall. Felt like it was riding on my fingers a little bit. And that's a 25.9. Where am I here? So 25.9, which would make then a 5.9. And one final measurement for the first half is to say, let's bring up to here, let it go. And this is a 26.1. And so a 26.1 makes a 6.1. And I'll say it one last time here then. Average these three, put that here. Average these three, put that there. Take that data, put it in your graph, and hopefully yours will look at least, well, somewhat close to this. If yours looks maybe a little bit more like this, call it a straight line. Okay? And so a lot of times that's what I see on a face-to-face setting as I'm walking around here. Hey Ron, I bumped my mic. Can you just see if I'm still on? And I'll assume I'm on. Am I on? Good, okay. And so there, is just make it a straight line. So if we're reasonably close, like I said, with our homemade equipment, let's call it close. And so if nothing else, when you finish up today's lab, you'll at least hear these words, that the gravitational potential energy is proportional to the height, and that the equation over there is the valid one that we were going to use and talk more about in Chapter 7 when we get to the principle of conservation of energy. All right, so let's head into Part 2. What is Part 2? And as I mentioned, as we were getting started, Part 2 over here is to change the mass without changing the height. And what you'll see in this table is the first column says mass added. And the first one is 0, and then it goes 100, 200, 300, 400, and 500. And what that column means, if we come back over here to the equipment, is this, that it's how much are we adding to the hammer itself. And so when we say 0 added, this is what we mean. We don't mean that the hammer, or the driver is what I should keep calling it. But the driver here is not massless. It has some mass. In fact, this mass is about 220, 225. But the neat thing here is we don't need to know what the mass is in order to see if it increases in a proportional way. So without taking this apart, we have no way of getting the mass. And we don't want to take it apart because that fouls everything up. So we're just going to say, let's start with no mass added. And I'll emphasize, no mass added does not mean no mass. No mass added means we probably have a mass of about 225 grams. All right. So this is my first setting right here. No mass added. And as you look here, you'll see that there's a column that says, okay, what is your initial dropping height? More on that in a second. But your fall distance must be 20. And it's just typed right in there. You have no way of doing it. And in fact, as you look at this chart, you will see that the fall distance is always 20, which is why it fits this concept here of part 2, to always drop it from the same height. Now, here's a part that's hard to explain to students as they do the equipment. It's easy to see somebody else. So I think this will be an easier time for me than in the past, where I have to kind of go around and kind of explain why you have to do what you have to do. But maybe you can appreciate the dilemma that I have here. When it says the initial height, this initial height must be something less than 20, so that when it falls and it moves the rod, the total distance is 20. But now you can see the dilemma here is, how in the world do I know where to put the initial height? Because I don't know how far the rod's going to move. How in the world am I going to know it's 20? About the only thing I know is it's less than 20. I mean, maybe it's 19. But if I put it at 19 and the rod does not move 1 centimeter, then I don't get 20. And you're right, you don't. So what we're going to do is this. Watch this carefully. Let's see, I did reset the rod, good. And if I look